It's my pleasure to introduce our next speaker, Dr. Elham Fini. Dr. Fini is an associate professor at Arizona State University, an invention ambassador at the American Association for the Advancement of Science, a Fulbright Scholar of Aalborg University of Denmark, a senior sustainability scientist at the Global Institute of Sustainability and Innovation, and the director of the Innovation Network for Materials, Methods, and Management. Her research focuses on the production, characterization, and atomistic modeling of sustainable novel material for use in construction. Her research has been featured by BBC Women in STEM, Science Nation, Wired Magazine, and CNBC. She is editor of the ASU Journal of Materials and the Journal of Resources, Conservation, and Recycling. Welcome, Dr. Fini, and the floor is yours.
Thank you. Thank you for the introduction. Glad to be here. It's my pleasure to talk about some of the work we have been doing and encourage some of the scholars and audience who listen to this talk to join us to help protect the planet and produce new products. With that, the title of the talk is actually End-of-Life Plastics to Enhance Sustainability of Pavement Construction using a hybrid method with bio-oil and carbon. The title is quite, wordy. So I guess I'll spend a few seconds to tell you what it involves. Obviously, we're talking about waste plastics, end-of-life plastics, what you all familiar with. I know you have been, you come across a bottle of waters every day and other sort of form of plastics, but we don't typically think what happens to this at the end of its life. Where does it go and how long it would take for it to degrade? And does it hurt the planet? Does it hurt anyone on this planet? So that's the question that we'll talk a little bit about today. And of course, the second part of the title is talking about sustainability of construction. Ideally, or I guess traditionally, these two have nothing to do with each other. But if you think about a waste from one industry could be possibly become a value-added product in another industry. That's sort of killing two birds with one stone, I would say. So what we have been working on this topic, and I'll tell you more about the technical side of it, is can we use end-of-life plastics, which are made from petroleum, mostly petroleum-based products, into some added value product for construction? So I'll go through the technical a bit. And of course, this disclaimer and sort of basically the statement that this work I'm talking about is published partly in the following two articles. It's also covered by a provisional US patent application. Anyone interested is welcome to contact me for detail, for data, for the actual articles and whatnot. But that's just basically a disclaimer. So getting to the talk, I guess they say a picture is worth 1,000 words. So just looking at this graphic art that was actually created by my sister, she's a graphic artist. It's talking about plastic, and you can see this fish running away. I guess you can see how the plastic, fish, the little plastic fish here, they actually make this big one go away or run away. And that makes a lot of sense when you think about 19% of the plastic produced worldwide end up in ocean. Can you believe it? So those 19% plastics, they don't belong to the ocean, but they end up in ocean now. And they actually poison and end up killing many of the fishes, or end up in the fish that we ultimately digest and maybe at some point become part of our food chain, which is definitely a no-no. But obviously, we're not talking about medicals and all this that are outside of our expertise, but just think about what if those plastics could actually be turned into a material that could help somewhere else, not hurt the ocean and the planet. So starting to talk about where the end-of-life plastics go, I just put a pie chart here so you get a better feeling of like what are the end of life plastic. So here we can see that some portion of it, almost 12%, this light green here, is the recyclable. Well, that's better than nothing, but almost 40% of it end up in landfill, the dark green. We also have a bunch of other type of recycling. We do actually incinerate a lot of it, and we have planned some of it is basically not in the counting, is lost through the process. But look at the big number here that is landfill, 40%. And we used to send, I guess in the US, some of it used to go to China, and we are not sending it anymore. And now we are more intensively looking at added value applications. Think about plastic, where it comes from is mostly petroleum based. So what if we could actually turn it and recycle it to its original building blocks to use it again and again, instead of reusing it, instead of making more new product. So there is an urgent need, really, to get this 40% here out of this pie chart and turn it to application. So the supplies are there, and you may think of it as a no-brainer, so why aren't we doing it? Well, some of the plastic are quite hard to recycle. So here is some of the methods that we do use today. For instance, making crude oil and use pyrolysis or thermochemical liquefaction, which actually we do also that in our university in the group. We make oil, but it involves a lot of heat and processing to get those oils. So energy that goes into it to make the crude oil. Other methods are biodegradation using microbes and fungi. I put some of the references for those interested in digging and diving deep in this topic. Another method is the hybrid method of fungi and irradiation. Sometimes we use microwave, UV, and other radiation to degrade the plastic. And there are a bunch of other methods that I didn't mention it here because maybe they are not as prevalent in the industry. And the final is surface treatment. Many people now they're trying to actually use surface treatment to be able to use the plastic in other format. And the talk I'm going to tell you about today is also part of the surface treatment, which my PhD student and who is now my postdoc in my group is actually working on surface treatment. We actually work with Thermo to get some of these experiments done. So thanks for their help. We actually published this work in a paper in journal paper, which I mentioned in the disclaimer in case you are interested. So I mentioned we do process some of this plastic, but some of these are quite naughty. We can't really recycle them easily. So I put a table here for those who may be new in the polymer and plastic arena. Just look at this table here. We have the name and the first column. You can see PET, HDPE, and so forth. And at the last column, I mentioned which one is recycled or it's hard to recycle or it's not recycled. So PET, HDPE can be recycled. PVC, LDPE are limited. And when you get to polystyrene and polycarbonate, they're much harder. And they are in different applications. You can see in this column here, the uses. For instance, the first one, PET, is what you use in the water bottles. You know, all those bottles you see filled with water, they are made of PET. You can see other applications like soap bottles made mostly from HDPE, plumbing pipes are from PVC, and so forth. So you can name them plastics, but they're really different types. So maybe it's not fair even to use the general word of plastics for all of them because they are really different animals. So when you talk about recycling, most of the time we are talking about breaking the plastic into its original monomer and then make new gadgets, new products with that. So that's ideal, because imagine if this is the building block of each of this, you know, this formula is the building block. If I to get this one back, well, I can polymerize it again and get the brand new HDPE. Well, getting the monomer out may not be as straightforward, and sometimes in the process of creating the monomer, we actually degrade the whole thing. So some of the methods I mentioned, we actually also do in the lab involve pyrolysis and thermochemical liquefaction. We get oil, but most of them become, most plastic turn at that point to oligomer, and many of it are heavily degraded. So the process we are talking about here today is to minimally degrade the plastics. We're not breaking it back to the monomers. We are actually using them as a compatible product for construction. So those of you who are familiar with construction, you see like a piece of roads you drive on, or the walls in your building, you know, where you're sitting, the floors, mostly made out of aggregates and some sort of glue, which could be cement, that put things together. On the road application side, we again have stone aggregates, which could be granite, limestone, sand, whatnot, plus a glue, which in that case for the road application is mostly asphalt, which is that black gooey product that keeps things together. So we thought these granules that are made out of plastics, if they are compatible with the rest of construction material, they could actually play a role as a building block and be part of the whole construction. They won't be released to the environment. Plus, they are pretty durable. If you imagine, one of the reasons that we are dealing with this huge plastic problem is because they actually take long time to degrade, over 100 to some 300 years. So they are durable. And in this case, we thought if we can use this as a granules that are compatible, maybe it works for the durability of the road. So here is the process that we use. We actually get mixed plastics, which is very hard to deal with because, as I mentioned, each of those plastics are different animals, and also these are colored. So most recycling companies don't like to deal with colored plastics, which make it even more cumbersome. So we don't mind, because the wall in your building could be grayish or maybe, you know, bluish or brownish. People don't care as much if the color is a bit different. So we can use mixed plastic here. And the mixed plastic is treated on the surface with an oil to make it compatible with the rest of building material. So in this scenario, we treat it with this waste vegetable oil in this bottle, and then we apply a bit of radiation. At that point, we grind it and we get these granules that you can see here. So from this product up on the left, we get this one on the bottom right. And this product can be directly added to construction of the concrete or asphalt roads. I'm going to talk a bit more on the asphalt roads, because you can think of, in America alone, we have 4 million miles of roads. And if we manage to use it safe and sound in the road construction business and improve the durability of roads, it's quite a win. And we can use a lot of plastic in that way. So what we made here, we called it oil treated plastic granules. It stands for OTPG. So OTPG is basically those granules that are that can now go into the construction material, either asphalt or concrete. So I show you a bit of characterization on this plastic. You know, the process is not really complicated. Of course, there is a lot of science behind it on how to make sure we get the right surface properties, but ultimately for a scale up and application, it seems pretty straightforward. And the source, the supply, is it's pretty much abundant. So here is the starting point. Is not treated, it just comes as is. We treat it with oil here in second picture. We grind it to the exact right size, and in the final part, we actually hybrid treated it with carbon, which made it super compatible. Both C and D pictures here, both products are compatible with the construction material. The one that has carbon coating has certain additional benefits, which I'll talk about in a minute. So the one that has carbon, we call it hybrid because it has oil followed by carbon coating. The one that is just oil, we call it OTBG, which is just oil treated. Both oil treated and carbon treatment, it helps with compatibility. So obviously someone may think, oh, why don't I just grind this first mixed plastic and dump it into the construction material? Well, the problem is segregation, because the plastic doesn't like cement or asphalt by itself, and they're gonna separate. So as soon as you're mixing and placing it down, your plastic will go to one side and the rest of your material will go to the other side. You don't want that. You want a very nice homogeneous mix. And that's why we have to make the plastic to like the rest of the material. And to do so, we use the oil treatment and in some cases, carbon coating. So just some of the science behind it and the characterization we have done. Here you can see the green is just the neat plastic, grinded, no treatment on it. And then the red is when we actually use the oil treatment on the surface. We basically use biografting to have certain biomolecules of the oil be attached to the surface of the plastic. And then the hybrid, which is HTPG here, is the one that has carbon coating on top of that. So if you can look at here from in the region of 7 to 721 to 1713, you can see here that the peak intensity here is reducing. There is a reduction in that region here from this to this to after treatment. On the other hand, in this region, we can see an increase and a sharp peak appearing, which may indicate the crystalline nature of the treated plastic. So the green is not treated, and as soon as we treat it, we get these structures forming. A sharp peak here in this range, you can see, is indication of the crystalline structure. So we know that with this treatment, we make the granules be even more crystalline. And on the other hand, it helps us with the structure of the whole composite when we have more crystalline plastic. But that was not the main focus. As I mentioned, the surface treatment and making it compatible was the first goal, but we got this added advantage of more crystalline structure. Here is the Raman spectra, which we got with the help of Thermo Fisher colleagues. They helped us get some of this data and analyze it. Of course, they are on the co-authorship of the paper as well. So this one, the ratio of the 1095 peak to 1115 is 1.3 for non-treated and 1.6 for oil treated. So you can see the increase here. And they also have a shift in this, which is another indication of crystalline structure. We needed to figure out what happens to the plastic structure itself, because at the end, we need to analyze the composite and figure out what's the role of these new granules, which is non-traditional. Like typical building, we never use plastic granules. So we had to know exact properties of these granules to predict the behavior in the construction. And one other characteristic that was very important was the surface property of this granules. As I mentioned, plastic itself doesn't like construction material, doesn't like cement or asphalt. In this case, we actually changed the surface energy. You can see from 91 before treatment, this is the neat sample, to 142 after treatment. So this 55% increase in the surface energy, in the dispersive forces, that shows the interaction would be enhanced when we mix it with other construction material. And this was a strong evidence or motivation that if we can increase the surface energy by this much, then we should be able to make it like the rest of material and not to separate, not to segregate. So let's see if it worked. So we increase the surface energy with oil treatment by biografting the biomolecules on top of the surface of the plastic. So literally your plastic now is carrying all these biomolecules around it and is not the same as typical plastic, is basically hosting all these biomolecules on the side of it, around it. So the first test we actually did was the segregation, because we wanted to know if this plastic would like the rest of the material. Here you can see if you actually put the neat plastic, like you just get a bottle of water and grind it to the right side and put it in asphalt for road, that's how much segregation you get. And it's terrible. So if you get this much segregation, ultimately, as soon as you place your road, this material will separate and your road will start cracking and falling apart. So separation index, or what we call it as SI here, is 132%. That was too high, and no one will accept such a high segregation and will not be approved even for the road construction. When we did the oil treatment, we end up getting 18, and with the hybrid treatment, we got 25, which was way much better than what we started with, which is another evidence that the surface energy did its job. So look at this again. When we changed the surface energy from 91 to 142, we made them to like asphalt much better. And that's evidence here. So we make it to go from 132 to 18 just because they like each other. They don't want to separate anymore. And here you can see we reduce it to 18 and 25, which is 86% here, improvement and so forth. Carbon was a bit higher, not that much, but a bit higher because the carbon coating literally covers some of the biomolecules and reduce their efficacy, because well, they are not seeing asphalt, they're covered, they are blinded by carbon on top. But still it works fine, 25. So then we had to do all the characterization in terms of performance. So here viscosity, which I put the ASTM standard in case you want to know the exact detail of the test, is a standard test. We use it all the time. Road authorities, they use it for the quality control, quality assurance all the time. So here we actually test the flow of the material. You need to be able to mix and compact and place it. If it's too stiff or it's too fluid, they're not good. You want the right range. So here we can look at the material that was neat. These are neat plastic, which we already showed is pretty bad. And it's not going to be accepted because of segregation. But still, we went ahead and tested in terms of viscosity. So the viscosity was around 6,000. When we used the oil-treated, the bio-grafted one, it actually reduced significantly. The yellow columns here is the oil-treated, and the green is the carbon-coated following the oil treatment. The standard temperature that we use in road application is 135 C. So any number in 135 C is the number we look at. And here, the red is just too high. Green is a bit high as well, but the yellow here, the oil-treated, meet the spec. So it could be approved just based on this viscosity here. Of course, there is a bunch of other tests to make sure it meets the road authorities' requirement, but that's one test here. So the test is run at 20 RPM. We apply shear and we apply torque and measure the resistance to shear. So the resistance to shear, then it's converted to calculate the viscosity value for each material. Other tests are also required in super pave specification, which is the code we use in asphalt industry, requires to check for cracking and for the fatigue. You can imagine, I put it here as fatigue resistance. You may think, what is fatigue resistance? Well, think about the traffic. As the car keep passing on the roads, they make the road fatigued. And we want a good resistance against that repeated loading. For that, we have this measure, which is a standard used in super pave specification, which is G star multiplied by sine delta, is a rheometry characteristics. We basically measure that and then compare it for different samples. It's simply, again, you can see the red, the yellow is the oil-treated one. And the neat here is the asphalt that doesn't have any plastic. So this is basically just what you use today on the road. And you can see this is 34. We got with plastic, with all the benefits that we will talk about with having plastic in, we just got 38, so very close. And here it says a lower value is preferred. So with the green, we even got a lower value than this. Of course, the red was way too high. I'm just putting the red here, even though it's rejected at the very first test, just to have a comparison and a benchmarking, but this won't be accepted because it's not compatible. So here you can see also for another test for the rotting resistance. Well, let me finish this. For the improvement of fatigue, you can see if this is 34, you get 22 here, you get significant improvement in the fatigue. That means based on this measure of fatigue resistance, the one that has oil treatment is a bit worse, but the one that has carbon treatment is even better in terms of fatigue. It means it lasts more cycles before it cracks. It means more traffic before it cracks. So in the second picture here, you can see G star divided by sine delta, and that's a measure of rotting. You may think of what is rotting. You have seen all those sagging area on the roads, the depression under the traffic, or the tires pass. As the car pass, you can see there are a bit of depth difference, a height difference on the road. That's called rotting. Of course, we don't want to have excessive rotting. It's dangerous. It can promote or cause hydroplaning. That's not good. And we want a high number in this case. So a higher value of G star over sine delta can be more desirable for fatigue, for rotting resistance. Here you can see that the carbon one is way more than everything else. The oil treated is still better than the neat asphalt, which is what we use today on the roads. Because we added these plastics, the rotting resistance went up and is expected. But the carbon treated was way up here and way down here. So that was sort of the best scenario in the fatigue resistance and the best scenario in the rotting resistance, which was impressive. So here we got 50% more stiffness and resistant to rotting compared to the other sample, compared to untreated. Then you can think of, okay, you talk about all this rotting, fatigue, and whatnot in the regular temperature, like in a regular day, maybe a summer season or whatnot. What happens when I'm very cold season, like in winter in Minnesota? What about that? Does the plastic make the road crack more or less? So we have another test for that, which is actually for sub-zero temperatures. Here we actually test the sample at -12 centigrade. And we measure their stiffness. That's another ASU standard. It's a standard test used by road authority in all 50 states in America. And we look at the two parameters. Here it says for resistance to cracking at sub-zero temperature, we want low stiffness, which is the yellow curve, and we want high M value, which is the blue curve. So we want the blue as high as possible and the yellow as low as possible. That helps us to resist cold winter of Minnesota for the road. So in this case, you actually see that the hybrid performed pretty well. Look at the M value here and the stiffness. The stiffness is pretty low, which is good. That means more resistant to crack. And M value, which is a measure of relaxation or ability of the road to release the stress. Because if it doesn't release a stress, much like human, if you accumulate a stress, you're gonna break down, right? So the road, if it accumulates a stress, it's gonna break down. M value is a measure that tells us how fast the road can release the stress by within the material. So here you can see that the hybrid had the best performance. You may say, well, neat was as okay. Well, remember, neat already rejected in other scenarios. And besides, we are looking at everything together. So we want high temperature performance, like a regular summer day in Arizona, or even in Minnesota in summer. So here, the hybrid was the best. Neat was not the best. And again, here, for the low temperature, relative to other samples, the hybrid treatment was pretty well. Here, the graphene coating, the hybrid coating helped big time with the stress relaxation, which was really impressive. You can see compared to these other two samples, you have higher stress relaxation, meaning it doesn't accumulate the stress to cause cracking. So with this series of tests, we actually got the performance characteristics. It seems it meets the criteria that we typically use. But then what about long-term aging? After the plastic is in our road for many years, is it going to age the same way? Like, I'm sure you have seen a brand new road, beautiful, black, smooth, and you have seen an old road full of potholes and cracks and so forth. So what about the plastic road? Does it make it less aging or better in resisting aging or worse? So here we actually did the accelerated aging in the lab, and we exposed it to harsh UV, ultraviolet radiation. And that's actually pretty relevant in summer season. And if you imagine the summer of Arizona, where I am from, it's actually quite intense in summer. So we get 320 days of sun, and it's pretty intense in summer. So those UV aging actually make the roads damage or age pretty fast. So we did that in the lab, and we compared the neat with the plastic ones. So here you can see the one that has plastics, regardless of what type of plastic, it aged much less. So the yellow is the road that we have today, the asphalt that we use in Arizona today. And you can see how bad it aged within this number of hours. So 200 hours, let's say, under sun. Of course, this is lab measure. So 200 hours in the UV aging exposure. This is the yellow is the current road. That's how it aged. And the yellow and the green and red is when we added the plastic, with the green being the oil-treated plastic. We also did the thermal aging. So what if the sun is not that bad, but it's very hot and is oxidizing? So we tested, this is another test in the lab without UV radiation, just thermal oxidation. And we saw the same thing here, the neat, I mixed up the color here, so don't worry about comparing the two figures. Here, neat is green. So if you can see here, the neat, and then the plastic ones, when it's unaged and when it's short-term age is the middle, and this one is extensively aged, like an old road. So imagine an old road. This one, the first bar, is the current Arizona asphalt. The second two bar is the one that has plastics, with the red being the one that we treated it. So oil-treated one. The aging difference, just look at this PAV, which is representing an old road. Let's say road at the end of its life. You can see the amount of aging difference if you have the plastic and if you don't have the plastic. So imagine how old is this one compared to this? Almost twice. So if I want to exaggerate on the numbers, there is no one-to-one correlation. But if this green represents a 30-year-old, I would say that the red is like half of that age. So it's much younger, even though they went through the same aging. So much better resistance when you have the plastic, which sort of made us think of the question that why the plastic helps and how it helps. And for that, we went actually to do a little bit of chemistry and figuring out what is doing what. So here is on the top, you can see the molecular structure of the plastic that we use here, PET. And then the oil, here are the molecules of oil that we grafted on top of this plastic. And we know that as the asphalt age and it gets older, it becomes like grayish. If you have seen a brand new road, it's more black, and as it gets older, it's more grayish. So some of its material are running away. some of its molecules are running away. So we actually did a study to see which molecules are running away from our roads, and here are some of the molecules that leave the road during its life. So we thought if we can keep these molecules in the road instead of leaving and going to atmosphere, to air, wherever, then maybe we can delay the aging. And maybe that's how we can explain this significant improvement right here and right here. So we looked at the molecules of PET. This is the PET covered or biografted. This is oil grafted one. And these are the molecules of asphalt that run away through its life. So as they run away, your asphalt gets older because it loses some of its essential components. And these are essential for the life of the road, but they leave. So here with this mechanism, the oil-treated one actually keeps these molecules in the road by having a good interaction energy with them. So this last part of the study is still being completed, and anyone interested is welcome to contact me for more information. But overall, we found that actually including the PET or end-of-life plastics in asphalt roads helps, provided that it is compatible. So I want to make sure this qualifier is there, because you cannot just grind and dump plastic into the construction material because they're not compatible. And they're going to separate, segregate, and it will be a disaster. So I would make sure if we are using end-of-life plastics, we make sure that it's compatible. And that's what I put in the first bullet here. We show that oil treatment, it improves crystallinity of PET, so you actually get a better granules than not treated one, which then it gives you a better stiffness and better properties in your composite. We also show that this whole improvement is attributed to the biografting, which increase the surface energy dispersion forces after oil treatment. So 86% reduction in segregation was observed in this scenario, and that was attributed to enhancement of surface energy, surface interactions. And reduction of segregation is exactly what we need to be able to use plastic within the construction material without they rejecting it. By rejecting it, I mean separating. So this is very important, and 86% reduction was pretty impressive. And the next step was hybrid treatment, which also showed the graphene coating hybrid with bio-oil coating. It actually helped improve resistance to cracks, especially at low temperature, which is very important in the states that get very cold winter. And overall, introduction of the oil-treated plastic help resistance to aging, whether ultraviolet or UV aging from the sun or thermal. It helped with both type of aging. So it can be significant improvement in extending the life of pavement, again, provided plastic is compatible with asphalt or cement or construction material and doesn't leach out and leave the construction. The compatibility is a key to make sure it performs well and is durable long term. So I wanted to also make sure, because this is sort of out of box, I guess, turning plastic to a construction material and maybe having roads and buildings from it. I want to also emphasize that we have something at ASU called ICU, and this is not hospital ICU, it's actually invention culture by you. So many of this invention that you hear and the talk that I discuss here is actually generated by students of mine who came up with these brilliant ideas, and as I mentioned, is now being protected by few provisional patents, and they all came from ICU. So any of you who are interested to work with ICU and join us, ASU has this open innovation platform, so you don't have to be a student or a faculty at ASU to work with us in ICU. If you're interested, just email me to get more information on it. And we love to see more invention and innovation coming in the business, in the construction, and overall to help the planet. And with that, I'm going to finish with my motto, that is, let's turn what stinks today into what sticks tomorrow. And I think with what I told you today, plastic is quite stinky, especially if it ends up in ocean and kill our fish. So if you want to innovate, or if you want to help the first-time inventors, I put 3 logos here. With the middle one, National Academy of Inventors. They actually have fundraising for first-time inventors. If you go to their website under donate button, you can actually donate to enable first-time inventors, like my student who actually did this invention on the plastic to asphalt application. With that, I stop and see if there's any question.